Hello everyone, welcome to this learning platform. I am Dr.I.Rama, Associate Professor, PG and Research Department of Chemistry, Sithalakshmi Ramaswamy College. In this session, we are going to derive the Schrodinger wave equation, one of the most fundamental equations in quantum mechanics. It connects the wave nature of matter as proposed by de Broglie with the concept of energy and probability distribution of particles. This Schrodinger wave equation was developed by Erwin Schrodinger in 1926, addressing the key limitations in Bohr's atomic model. Motivated by Heisenberg's uncertainty principle and de Broglie's wave-particle duality, Schrodinger formulated an equation, wave nature of matter. The electrons behaves as waves. This was the concept of de Broglie. Taking up this, Schrodinger developed a mathematical equation. This equation is rooted in probability and views the electron as a stationary or a standing wave around the nucleus. Consider a stationary wave associated with the electron. That electron is traveling in positive direction of the x-axis. It has the momentum of px and total energy E. Now, the classical wave equation for this stationary wave is given by psi is equal to a sine 2 pi x by lambda, where psi is the wave function, x is displacement of wave along x-axis, and a is the maximum height of the wave and lambda is the wavelength. On differentiating the equation with respect to x, we will get the equation 1. On differentiating psi, we will get d psi by dx. A is constant, so it is kept as it is. Sin theta will become cos theta. Differentiating this sin theta, it will give us cos theta. Instead of theta, we are having 2 pi x by lambda. So, the 2 pi x by lambda is written here. Now, this 2 pi x by lambda having x is to be differentiated. On differentiating that, we will get 2 pi by lambda. X will become 1. So, this equation 1 will be obtained. Rearranging this equation, we will get the equation 2. Now, we are going to differentiate the equation 2 with respect to x. The same procedure we can follow. So, the final equation which is being rearranged is equation 3. Here, we know that psi is equal to a sine 2 pi x by lambda. Already we are having equation 3. In which the a sine 2 pi x by lambda can be replaced by psi. On substituting instead of this term, we get the fourth equation. D squared psi by dx squared is equal to minus 4 pi squared lambda squared into psi. All microscopic particles such as electrons, protons, photons, etc. According to de Broglie's equation, lambda is equal to h by px. We all know that. What is px? Px is momentum, which is the product of mass and velocity. So, we can replace px with the mv. Now, we are squaring the equation 5. On squaring the equation 5, we will get lambda squared is equal to h squared by m squared into v squared. That is what the equation 6 is. And now, this equation 6 is used in equation 4. What is equation 4? This is equation 4. The equation 4 is dou squared psi by dou x squared is equal to minus 4 pi squared lambda squared into psi. Here the lambda is replaced with the value which is found out in equation 6. On substituting this, we will get the equation 7. We all know that Total energy is simply the sum up of kinetic energy and potential energy. Then the total energy E is equal to half mv squared plus v. Now we are rearranging the previously seen equation, that is E equals half mv squared plus v. This was the equation. It is rearranged and finally we arrived at mv squared is equal to 2 into E minus v. This is equation 8. Now we are going to combine the equation 7 and 8. So we got this equation 9 and this ninth equation is rearranged. So this is equation 10. This 10th equation is nothing but the Schrodinger's wave equation for a particle moving in one dimension, that is along the x-axis alone. If the particle moves along the space, that is it moves along the three-dimensional space, then the equation will become dou squared psi by dou x squared plus dou squared psi by dou y squared plus dou squared psi by dou z squared into 8 pi squared m into e minus v by h squared into psi is equal to 0. So the equation for the particle moving in three-dimensional space is shown here, and this is equation 11. This is the Schrodinger wave equation in space for a single particle. Then later, these terms, instead of d squared by dx squared, we may use dou squared by dou x squared. Similarly, for all the terms, we can simply replace d by dou. Then we got this equation 12. In the 12th equation, the terms dou squared by dou x squared, dou squared by dou y squared, dou squared by dou z squared, all are called as del squared, which are simply the Laplacian operators. Then we can replace that terms with del squared into psi, and we finally arrive at the equation del squared psi plus 8 pi squared m by h squared into e minus v into psi is equal to 0. This is equation 13. On continuation of the Schrodinger wave equation, we are going to discuss about the Hamiltonian operator form also. For this, we had taken the Schrodinger wave equation, which is derived previously, and then we are expanding the equation. Then it will result in the expanded form of the equation. And this equation in which one term contains E, another term contains V. The V term is kept in the left hand side and E terms are totally moved to right hand side. Now we are going to divide the whole equation by 8 pi squared m by h squared and we get this final equation. Now multiplying the equation with the negative sign, we get minus del squared psi into h squared by 8 pi squared m plus v into psi is equal to E psi. Now we are taking the psi outside because the psi is common in these two terms. So psi was taken out and the equation is rewritten as del squared into minus h squared by 8 pi squared m plus v into psi is equal to E psi. Now this term will be taken as h, which is a Hamiltonian operator. Then h into psi is equal to E into psi. This is equation 14. And this equation is called as Hamiltonian form of Schrodinger equation. So far, we discussed about the derivation of Schrodinger wave equation, which is time-independent Schrodinger wave equation. We have seen two forms. One form is general form, another form is Hamiltonian form. The key takeaways of this Schrodinger wave equation is it links the wave function psi to total energy of the particle E, as well as it explains how particles behave not as points but as waves of probability. Then the equation forms the mathematical foundation of quantum mechanics, allowing us to describe the atomic orbitals, energies, and behavior of subatomic particles. Thank you for joining me today. I hope you found this discussion useful and easy to follow. Keep exploring, keep questioning, and see you in the next video. Thank you.